Okay, now I'm going to introduce you to a second notation. It's called vector notation. We did bracket notation already, and this made it easy for us to extract the probability of measuring each possible state and knowing the phase. Okay, so just a reminder that the probability of measuring 0 in this case is absolute value of a squared, and probability of measuring 1 is absolute value of b squared. Okay? Now, let's look at vector notation. Vector notation you might think is no different, but it turns out that vector notation is really important for making the calculation of gate operations. So we're going to store it as a vector. What is a vector? A vector is just a way of storing a list of numbers, of depicting the storage of a list of numbers. So we can see we have sort of a long bracket here. I make it as tall as I need to hold as many as I want. Well, we will always be holding for a single qubit, we'll be holding 2 because there are 2 possible states with a single qubit. So I just make the brackets up here tall enough to store these 2 values. And so I always put the probability amplitude for the 0 on top and for the 1 on the bottom. So the only confusing thing that I find with this is that the reason the bracket was so nice was because I had the 0 in the ket and the 1 in the ket, and so I knew that A was square root of the probability of measuring 0, and B was square root of the probability of measuring 1. But in this case, well, though it could be positive or negative, but with the vector notation, we lose that visual reminder of where the position is for the amplitude corresponding with 0 and where the position is with the amplitude measuring 1. So you're just going to have to remember that 0 is always on top and 1 is always on the bottom. And in fact, when we get to having more, it's just always in increasing order as you go down. So 0 is the smaller number, it comes on top. And so just think of it as smallest to largest from the top to the bottom. Okay. All right, so if I had others, this is also why it's really important that when you do it in bracket notation, you always put the 0 on the left and you always put the 1 on the right. Again, I've got the A at the top and the B on the bottom. So if I were to do 1 over root 2, I would put the 1 over root 2 on top and 1 over root 2 on the bottom. Now these are equal probabilities, so it turned out that the order didn't matter, but normally it does. Okay? All right, so then we have this example. This example is the 1/4, 3/4, right? Square root of 4 is actually 2. So I have the 1/2 is on top and root 3 over 2 is on the bottom. So if I were to do something which I shouldn't be doing, which is putting the 1 on the left and the 0 on the right, then I would have to make sure, well, now it goes in vector notation in the opposite order. We don't want to do that, but I just wanted to illustrate that it's not just that the one on the left is always going on the top, it's the one associated with the probability of measuring 0 and the probability amplitude associated with 0 and the probability amplitude for 1. Okay. All right, so we also have algebra-like simplification for vector notations, and these ones we will do. So remember this bracket notation. So if I have 1 over root 2 and 1 over root 2, I can factor out this 1 over root 2, but I don't remove it, I just take it out of the brackets. Okay, so this we will be seeing in this class. What I didn't like about that simplification in bracket notation was that the 1 over root 2 disappeared entirely, and I don't like that. So in this case, we just pull out the 1 over root 2, which can make it a lot easier because the numbers get really small and drawing that root 2 sign gets really small. And so it can be much more legible to pull out the 1 over root 2 and then to have 1 and 1 inside.